What is a semiconductor? A semiconductor is a material whose conductivity lies somewhere between that of a conductor and an insulator. A semiconductor's conductivity can also change based on its environment. For example, a semiconductor's conductivity changes with temperature. To better understand this, let's look at what happens at the atomic level. In an atom, there is a thing called the valence band, which is the outermost orbital of an atom. With enough energy, electrons can jump to what's called the conduction band. In a conductor, these bands overlap, which means it is very easy and takes very little energy for electrons to move in between these bands. But in an insulator, these bands are very far apart, which means that electrons will have a very hard time getting to the conduction band. In a semiconductor, the gap between the bands isn't as large, only about 1.12 electron volts. Another thing to look at in a semiconductor is this thing called the Fermi level. Now, the Fermi level is the maximum energy level that electrons will occupy in an atom. All right? At absolute zero, the Fermi level is called the Fermi energy. And in a semiconductor, or more specifically silicon, the Fermi energy is right in the middle between the valence band and the conduction band. However, one of the cool things that makes semiconductors interesting is that the Fermi level can be modified with temperature. So as temperature goes up and down, the Fermi level can go up here, and electrons will have an easier time getting across, or down here, where electrons will have a harder time getting across. All right? Now, this is the Fermi function, which describes the distribution of electrons above and below the Fermi energy. E equals the energy level, EF equals the Fermi energy, aka the Fermi level at absolute zero. K is the Boltzmann constant, which is about 1.38 times 10 to the negative 23 joules per Kelvin. And T is the absolute temperature. At T equals 0, when we graph the function at T equals 0, we can see that below the Fermi energy, there is a 100% chance that you will find an electron. However, above the Fermi energy, at absolute zero, you will not find any electron. Now, if you change T to be greater than 0, then the distribution will change, and you will be more likely to find electrons above the Fermi energy. Now, another way to change the Fermi level of a semiconductor is through a process called doping. Doping is when you introduce impurities into a semiconductor to, make it more or less conductive. All right? Now, take silicon. Silicon has 4 electrons in its valence shell. All right? However, silicon wants to have 8 electrons in its shell. So what does it do? Well, when it meets up with other silicon atoms, it forms covalent bonds with them, and they share their 4 electrons, allowing each one to have 8 electrons. All right? Now, one way to change its conductivity is through doping, through introduction of impurities into the silicon array. Let's take phosphorus. Phosphorus doesn't have 4 electrons in its valence shell, it has 5. This means that while 4 of its electrons will join up with the 4 electrons from the silicons around it, allowing it to have 8 electrons in its valence shell, as is optimal, there will actually be another electron floating around the semiconductor. We call this an N-type doped semiconductor, as the semiconductor is, generally speaking, more negative. Now, what happens if we introduce a different material? Say, boron. Well, boron doesn't have 4 electrons in its valence shell, nor does it have 5. Actually, boron only has 3. So what happened? There is now an empty space, which we call a hole. And this makes the whole thing generally positive, leading it to be called a p-type semiconductor. Now, what happens if you put an n-type and p-type semiconductor together? Well, then you get a diode. A diode consists of an n-type and p-type semiconductor put side by side in what's called a p-n junction. Now, before any current is applied, the electrons at the edge of the junction will naturally travel from the n-type side to the p-type side to fill some of the holes. However, when those first electrons reach the other side, they create a negative charge on the edge of the p-type side and a positive charge at the edge of the n-type side. This creates an opposing electric field and prevents electrons from moving any further. We call this the depletion layer. And it is this property that makes diodes particularly good for switches. Now, if we were to apply a current with a sufficient voltage difference, say around 0.7 volts, then the electrons will be able to, on the n-type side, will be able to overcome the depletion layer and complete the circuit. We call this a forward bias. However, if you were to flip the source of current, then you will get what's called a reverse bias, wherein the depletion layer will increase dramatically and the electrons and holes will move to their respective ends. Like this, no current will go through, and it will require an immense voltage difference in order to bridge that gap. And it's almost impossible for electrons to overcome that gap. This is a transistor, or more specifically, a bipolar junction transistor. Like a diode, transistors contain p-type and n-type semiconductors. However, unlike in a diode, there are actually 2 n-type and 1 p-type semiconductors instead of 1 of each. The first n-type semiconductor is called the collector, the middle p-type semiconductor is called the base, and the final n-type layer is called the emitter. Like in the diode, the areas between the semiconductors form a depletion layer, wherein electrons are unable to flow. Likewise, electrons can only move if a current is applied and a sufficient voltage difference exists. The necessary voltage, however, varies with each region of the transistor. The collector region is highly doped, while the base region is very lightly doped. This means that it only takes a small voltage difference to allow current to flow. Meanwhile, the emitter region is medium doped, which means that it takes more voltage to allow current to pass through. This is what makes transistors special. The varied voltages required to allow current to pass makes transistors particularly good as amplifiers and switches. As amplifiers, transistors can take a small current in one circuit and amplify it into a larger current in the other circuit. Similarly, transistors make good switches with their ability to utilize multiple circuits at once. A transistor's switching properties are particularly important in microprocessors, which use the on and off states of transistors to encode information. However, if we're talking about computers, we should pick a different type of transistor. This is a MOSFET, or metal oxide semiconductor field effect transistor. A MOSFET, being a transistor, consists of 2 n-type semiconductors, called the source and drain, nested inside of a p-type substrate. Now, What distinguishes a MOSFET from a bipolar junction transistor is its potential size, it's quite small, and its method of overcoming the depletion layer. Instead of relying on a direct current to a base, MOSFETs have what's called a gate. The gate consists of a metal part and an insulator in the form of an oxide. A current is applied to the metal in the gate, which generates an electric field, hence field effect transistor, that allows the electrons in the source and drain regions, corresponding to the collector and emitter regions respectively, to overcome the depletion layer and allow current to flow. What are logic gates? In the previous section, we learned about how transistors and microprocessors switch on and off to encode information. You might have heard of this. It's called binary. Logic gates use binary to create more complex operations. At their core, logic gates are a series of transistors that use binary to encode information. There are three basic types of logic gates. First, the NOT gate. The NOT gate is simple. It takes an input value and outputs the opposite value. For example, input on, which we will call 1, and a NOT gate will output off, which we will call 0. Similarly, if you input a 0, a NOT gate will output a 1. Next, we have AND gates. AND gates are a bit more complicated in that they take two inputs and produce one output. In an AND gate, input A and input B must be the same in order to produce the same output value. Let's say that both input A and B are 1. The resulting output will also be 1. However, if input A and B are different, then the AND gate will produce a 0. And obviously, if both inputs are 0, the AND gate will output another 0. Finally, the last basic gate is the OR gate. OR gates will output a 1 if at least one of the inputs is 1. Input A or input B can be 1, and the output will still be 1. These basic gates form the basis for more complex gates, like NOR and NAND. A NOR gate is an OR gate followed by a NOT gate, while a NAND gate is an AND gate followed by a NOT gate. Increasingly complex chains of logic gates form the basis for how computers, quote-unquote, think. Think about it like a sentence. Each gate links together information the same way words like not, and, or do in English. By creating sentence after sentence consisting of these complex chains of logic gates, we can form complete thoughts and ideas just by using switches with two states, on and off. From sand to switches, silicon to transistors, humans have found very creative ways to utilize semiconductors and their unique properties. I hope you enjoyed this video, and thanks for watching.